Was. What is
Okay,
up?
now
Sorry
now we
about
can-
that, everybody. Thank you for pointing that out. All right, so what I was just saying is this problem is looking at a model that was found after sampling 200 students. 200 students were given a test every 6 months over a course of 4 years to see how well they remember Spanish. And the idea here is that, well, we can look at the scores, model the scores, and this will tell us something about how well they remember things over time. And then I jumped to the next slide, and I said, all right, what we're looking for is the rate of change here, because that's what the problem asked us. After 1 year, what's the rate of change? Then I jumped to the next slide, and I said, all right, we're told that looking at the solution, the derivative is 15.6, negative 15.6, I forgot the negative, over t plus 1. Now we're going to go back and look at the original function to prove this. So, applying the derivative, dp dt is equal to d dt on 1.6 minus d dt of 5.6, the ln of t plus 1. Well, this thing's going to be 0, right? Derivative of a constant. We can pull out this 15.6 because of multiplication with derivatives, right? Multiplication of constants, I should say. So this is going to come out to be 15.6 times whatever this derivative is. Well, this derivative is going to be 1 over u times the derivative of u, right? Well, the derivative of t plus 1 is just 1. So we're going to get 1 over t plus 1. And after we simplify, it does in fact equate to what we're given in the solution. Make sense? Now from here, since we're asked to solve at a particular time, at 1 year, and we know that time is measured in months, we want to plug in 12 for t and find out what the derivative comes out to be, right? I'm not going to do the algebra here, but I'm going to go back to that slide. T is equal to 12. Plug in t. We get negative 1.2. Percentages aren't negative though, right? So we just pull out the negative and add on that percentage sign. And we say that it's decreasing. Make sense? So up to this point, we've talked a lot about ln. And I've said in the past, in the last lecture, that phi to the y is equal to x if, I'm going to use some math jargon. What this means is if and only if. IFF is mathematician for I'm lazy and don't want to write out if and only if. If and only if log base b of x is equal to y. Right? Because what the logarithm's doing is saying, all right, assuming that your base is b, and the whole thing evaluates out to be x, what exponent do you have to tack on to b to get x? That's what we're asking here with the logarithm, right? And we said more generally, or more specifically, that log base e of x is written as the ln of x, right? So this is what we've been talking about up to this point. It's just the ln of x. But what about when it's log base anything other than e? What then? Well, we need to know a couple things first. First, we need to make sure we know how these things work. So let's consider a couple of these examples. Let's look at A here. A is asking, to what power does 2 have to be taken to for 2 raised to that power to evaluate out to be 8? Well, this is 2 to the third, right? So y has to be 3. Similarly, let me grab another color, keep everything separate. Let's say we've got log base 3 is of 81. This thing's going to be equal to, let's use another variable just because. Let's call it z. And let me not write it so sloppily so that it's easy to read. What this is telling us is that 3 raised to the zth power is going to be 81. What is that z? Well, looking at it, I have no clue right off the top of my head. But I know 9 times 9 is equal to 81, and 9 is equal to 3 squared times 3 squared, right? This must be 3 to the 4th. So z has to be 4. Is this sort of logic making sense? So, having said that, let's say we're given something like the ln of, I don't know, let's go with 64. I have no clue what this is. Like, I honestly don't know. But I know that this is log base e of 64. Let me actually go the other way. Let me use a different value. It'll be more clear based on what's on the slide. Let's say log let's go with 7 of e to the third. Again, I have no clue. Like, I can't look at this and tell you what this is. It's beyond me. But using the change of base formula, we know that this is going to be equal to the ln of whatever we're passing through our argument, right? E, in this case, e to the third, over the ln of 7. Well, hey, this thing reduces kind of nicely to just being 3 over the ln of 7. I still have no clue what the ln of 7 is, but this gets us going. This gives us a starting place. Back in the ye olde days, long before my time even, there used to be books, stacks of books that mathematicians would have that you could look up what logarithms were for different values. And they would use the change of base formula to jump between logarithms. I actually have like 2 or 3 of these books, and they're massive. I've only ever had to use one once for a class, and that was for an exam that the professor was like, you're not using the internet to look this up, but you're not calculating this by hand either. Here's this book of logarithms and integrals, figure it out. But, like I said, this gets us going. Now we can just type in the ln of 7 or whatever. And as a motivation for why we might care about this, I'm going to guarantee that almost none of you will have a log base 7 key on your calculator. So how are you going to evaluate that? Well, if you change the bases to something you do have, like log base e, then you can start evaluating it this way. Make sense? So having said that, let's consider this example here. Log base 3 of 6. Log base 3 of 6. Again, I have no clue what this comes out to be, even with base 3. But I know I can rewrite this as the ln of 6 divided by the ln of 3. I still have no idea what this evaluates out to be, but now I can at least put this into my calculator and say, all right, give me the ln of 6, give me the ln of 3, divide the 2. Comparing comes out to be a really asinine decimal. That's the technical term for that decimal sucks. Now, something I want to point out, we passed a negative through here, right? But negative numbers aren't in the domain of any logarithm. Doesn't matter what the base is, you can't put a negative through it. And the reason why is because what the logarithm's asking, right? Let's consider any base, log base b of -1. going to say this thing is equal to y. What it's answering is the question of what the exponent has to be for b raised to that exponent to come out to be 1, or negative 1, I mean. Excuse me. Doesn't exist, not in real numbers anyhow. Imaginary numbers, yeah, sure, okay. But let's not be extra. All we're saying here is that looking at real numbers, we can't put in a negative value through a logarithm. Doesn't matter what the base is. So jumping ahead, we want to see that the derivative, let me write it out like this on the board. So let's say we're given a function, f of x is equal to b of x. What is that derivative? Any thoughts without looking at the proof here? Well, it may not be obvious at first, but one thing we can do is rewrite b raised to the x as e raised to the ln of b, all that times x, right? Agreed? Might be a little bit more clear to write it like this. All right, so we can rewrite this now. And this thing, we can take the derivative of. We know that d dx of e to some function u of x is equal to e u of x times d dx of that function u of x, right? So when we're given an exponential raised to some random base, we can rewrite that in terms of e and say, all right, cool, d dx of b to the x is equal to d dx of e raised to the x ln of b this thing is like u of x, right? Yep. So this tells us then that d dx of b to the x is equal to e to the x ln of b times the derivative of u of x is going to just be the ln b. We can, of course, reduce this a little bit if we really wanted to be the ln of b times b to the x, if we really wanted to reduce it. And so we get to the derivative rule in other bases. When it's an exponential, the derivative rule is going to reduce to the ln of whatever your base is times a raised to whatever your general function u of x is, all of that times the derivative of that general function, right? Make sense? Now with logarithms, things change a little bit, but that's only because of the way that change of base formula works. So with logarithms, because we know that log base a of x is equal to the ln of x all over the ln of a. We now know that dx of log base a, let me keep with my, no, let me keep it like this. Log base a of x, this thing is going to be equal to the derivative of the ln of x over the ln of a. Well, the ln of a, that's just a constant. So let's pull it out. So what we're going to be left with now, after we evaluate this expression, is going to be 1 over the ln of a times 1 over x. So jumping now back to that spot on our notes, check it out. The derivative of log base a of x is 1 over the ln of a times 1 over x. And more generally, if instead of x, we had some general function u of x, there would be 1 over the ln of a times 1 over that general function of x times the derivative of that general function of x. Make sense? All right, so let's use this now. We're given this model that measures the amounts of gram left over after some radioactive carbon isotopes decay with time. So we're told that the amount left over is going to be 1/2 raised to the T over 5,130 something, right? No, 5,715. All right. I'm going to take the derivative of this. The derivative of this whole thing is going to be equal to the derivative of e to the ln of 1/2 times t over 5/715 This is going to come out to be e times the, or raised to the ln of 1/2 times the quantity t over 5/715 times the derivative of what's in our exponent right? So what we're going to get when all is said and done is e raised to the ln of 1/2 times t over 5/715. This whole thing times the ln of 1/2 divided by 5/715. Now notice I went the long way. I didn't just directly apply that rule. I went the long way to show how nice that rule actually is. If we had used the rule, we could have went ahead and skipped from here to the ln of 1/2 raised to the t over 5/715 times the derivative of just this part of the exponent, right? So that rule is actually kind of convenient because it cut down on some of our heads, on our work. Make sense? I'm going to go ahead and skip to the next slide now. And compare and contrast. Notice that's exactly what they did. They just went ahead and applied that rule directly. And then they found what the rate of change is when time is equal to 10,000 years. Now I want to make a point about these problems because I believe, if I remember correctly, I put them in your homework. If you were told in general, the half-life of a thing is however many years, then the formula, well, if half-life is k years, and you start with some initial amount then we know that the formula for the amount with respect to time is going to be equal to A naught times E raised to the ln of 1/2 T over K. All right, this is crazy, I know. Let me explain what's happening here. What this solution, what this formula is solving for, is it saying let me rewrite it as A naught times 1/2 raised to the T over K. What this formula is saying is that if the half-life of a thing is K years, then that means after that many number of years, you're gonna have half of what you started with, A naught. So if that's the case, then what we want in our exponent should be 1 after K years. Make sense? So we're going to have T divided by K. Now, if we go twice as long, then we're going to have a quarter left. So we should have 2 in our exponent, right? Well, twice as long for K divided by K is just going to be 2 in your exponent, right? Make sense what I mean? So the general formula for finding the amount of a thing left over, if it's decaying, if it's a radioactive substance decaying, is going to be using this formula. And I can make this a little bit better to read. So just know this for homework in case these problems show up, because I believe they do. Okay, so some more about just general details of exponential growth and decay. When we talk about exponential growth and decay, let's step back even further. The word exponential, I've already defined it once before. It means that it's proportional to its current state, right? Its future states are proportional to its past states. So when we talk about exponential growth and decay, we're saying that the change is proportional to its state. In other words, the rate of change, dy dt, is proportional to y in some way. Anytime we have problems of proportionality, this is going to be something is equal to k times something else, right? So just on vocab and vernacular, if A is proportional to B, then A is equal to KB, right? So since the exponential is telling us that this thing is going to be proportional in states over time, right? We get this equation. Does that make sense to everybody? Folks at home, does that make sense?
Starting to, yes.
Awesome. Cool. So, having said all of this, the way we solve these problems, they're going to show this guess and check method. They say, all right, we know that dy dt is proportional to ky, it's proportional to y. So we know that dy dt is going to equal some constant times y. Let's guess what y is equal to. We're going to guess that y is equal to some constant times e raised to the kt. And then they're going to check to make sure that it satisfies the equation. They're going to say, all right, we're guessing that y is equal to some constant times e raised to some constant times time. Now let's check to make sure it satisfies this. We're going to take dy dt Now evaluating the derivative on e to the kt, we're going to get c times k e to the kt. Well, hey, we can rewrite all of this, right? We can rewrite this as k times c e to the kt which is in fact equal to k times y. Now, I'm not a fan of this method. I understand why they show it to y'all, but I don't like it because it uses guessing and checking. So, I'm going to show y'all how it's actually solved. Having said that, I should note that what I'm going to use is something we haven't talked about yet. We're going to talk about in the next chapter. So when you look at this and you're like, wait, what? You should. That's okay. We're going to work through this though. Now, we're told that dy dt is equal to kt. I mean ky, sorry. If that's the case, then this tells us that dy divided by y is equal to k dt. All I've done here is I've divided y from both sides and multiplied both sides by dt. Now the boogeyman from next chapter is going to rear its head here. I'm going to apply what's called an exponential, an integral. dy over y is equal to the integral of k dt. Like I said, we're using material right here from the next chapter. This thing on the left-hand side is going to evaluate out to be the ln of y. This thing is going to evaluate out to be kt plus c. Now, before I go any further, what do you notice about this and what we started with here? If you took the derivative of this, you get 1 over y, right? If you took the derivative of this, you get just k, right? These integrals are antiderivatives. They undo the derivative in some sense. Like I said, we're going to go into this next chapter, but thought right now was a good time to go ahead and kind of ease us into it a little bit. So having said all of this, we want to take and raise both sides now, or rather raise e to both sides. So we're going to get e to the ln of y is equal to e to the kt plus c well, this left-hand side is going to become just y, right? And this right-hand side, notice we can break this up a little bit. We can break this up as e to the kt times e to some constant. Now I'm going to say here, let's go back and label all of our c's. So what we've got here is a constant raised to a constant. That's just going to be another constant, right? So let's call that C2. Which is exactly what we guessed. All right? Now there's a lot of hand waving here that I'm doing, like from here to here, here to here, here to here. These first couple lines, there's a lot of hand waving, and I'm just going to ask you to take it at face value for right now. But, like I said, as a good lean into the next chapter, one of the things we will be able to use the integral for is solving problems like this. Also, what you just did, what you just saw, was the solution to an ordinary differential equation, which is an upper level undergrad course called ODE, or Differential Equations, DiffEq. So congratulations, you just saw material and hopefully understood it, somewhat anyhow, from a 400 or 500 level course. So, all of this aside, we've got what's called the law of exponential growth and decay. All this law of exponential growth and decay is telling you is that generally, if you know that something's going to grow exponentially or decay exponentially, it fits this formula. If k is less than 0, you decay. If k is greater than 0, you grow. Pretty straightforward. And this makes somewhat some sense, right? Because e raised to the 0 power would just be 1. So presumably anything above 0 will make you grow, and anything below 0 will make you decay. So, some more on half-lives. just a common set of examples of different isotopes. U-38 decays really slowly. Nobelium decays really quickly. So using one of these examples, or using this example, we're given a sample of radium, 1 gram of it, right? Yeah. So we're given an amount of radium, A naught, equal to 1 gram. We're told that we're looking at radium. I'm just going to write it as K rad for the half-life of radium. Radium is equal to 1,599 years. That's the half-life of this. Five, 9, 9. Because of my half-life explanation, I wrote it like this. Now, using what I was explaining earlier, putting all this together, we're going to have AT, the amount with respect to time, is equal to A naught times E, or times 1/2, raised to the T over K, right? Plugging everything in. 1 times 1/2 raised to the T over 1,599 years. Now, they're going about solving this a slightly different way. They're saying that we know this thing's decaying exponentially. And if you didn't know this formula, you could go about solving it a slightly different way. What you could do is you could say, I know that this thing is decaying exponentially. So it's going to have the formula EKT as a generalization, right? This K is not the same K as the last one. I want to make that clear really quick. What we know is that AT at time 0 is equal to 1. So that tells us then C must be equal to 1. And we know that this is the case because this is what we start off with, right? Before this thing starts decaying, we said we have 1 gram. So at time equal to 0, we have 1 gram. Because AT is measuring the number of grams of this radioactive material we have. So we know at time 0, we have 1 gram. The formula is going to look like this. Well, when you put 0 in for time, all you're left with is C. So C must be equal to 1. This tells us that AT is of the form E to KT. Now, we're told that we're using radium. So at time equal to 1,599 years, we're going to have a half of it left, right? So this tells us then that E to the K times 1,599 is going to be equal to 1/2. So now we just want to solve for K. Take the ln of both sides, right? The ln of 1/2 is going to be equal to K times 1,599 . So K is equal to the ln of 1/2 divided by 1,599. Coming back up to our original equation, you know this whole thing comes out to be E to the ln of 1/2 divided by 1,599 times T, which we can simplify to 1/2 raised to the T over 1,599. They went about this a little bit different. I just want to point this out. They actually approximated what K is. But notice this is a really small decimal, and this is just an approximation. But what we have on the board is exact. Because, yes, sir.
So just like on like the homework or a test or whatever, would we do it in like the exact form, or would we do it like in the, or?
It's going to ask you to use a rounding.
Okay.
It's going to say approximate to so many decimals. Having said that, in a calculator, you could actually write the ln of 1/2 divided by 1,599 and keep it that way, and not have to worry about what this decimal actually is.
Oh,
Makes sense what I mean?
yeah.
So if there's error in how you rounded things, it doesn't move all the way through. The rounding would happen at the very end now. See what I mean? Cool. Is there anything else I wanted to say about this problem? No, there was not. All right. So the general guideline for writing these things out. You're going to want to do this in 2 steps. The first step is you're going to want to set up your equation. You know, with exponential growth or decay, it's going to look like this. And then you're going to be told a few different details. You're going to be told something about what the initial state is. It's going to give you C every time. And then you're going to be told something about some other time. Let's call this L. Let's call this, well, let's just call it what it is. It's equal to C, E, to K at L, right? And this is equal to E to K at 0. So using these 3 points of information, you know the general form, you know something about the initial data, you know something about the data a little bit longer down the road. You can solve for C and you can solve for K. So what does that all look like? Well, I'm going to break down into two different parts. In A, let me actually write it slightly different. The ln of A at L divided by C all divided by L is going to give you K. So I'm just trying to simplify these rules a little bit. Notice we can rewrite our numerator here to be the ln of A at L, so whatever that data is, minus the ln of C all divided by L. Make sense? So I'm trying to simplify this as much as I can so that some of these problems don't feel like they're coming out of nowhere. So for those who remember my rabbit description, we've got another problem similar to it. This one's fruit flies. We're told that they increase according to an exponential model. That after 2 days, there are 100 flies, and after 4 days, there's 300 flies. So here, the data is a little bit different. We have 200. Here we've got 4. And that's 300. How are we going to solve this? What do you all think? Let's make a quick observation. If I divided A at 2 by A at 4, or vice versa, let's go vice versa. It'll be a little bit nicer for the math. What we have here is that these C's are all going to cancel out, right? We're not going to have any of them left over. Instead, what we're going to have is E to the K at 4 divided by E to the K at 2. Well, this thing we know from our initial data is going to be equal to 300 over 100. And this is why I went ahead and reversed the order that I wanted to put it in. Okay, now let's think about these exponents for a second. We can rewrite them, can't we? We could rewrite this as E to the K at 4 minus E, or minus K at 2, right? All I've done here is use properties of exponents, right? I started by saying this thing is equal to this thing. And I should drop those parentheses so it doesn't get too confusing. Which is equal to e to the k 4 minus k 2, which is equal to 3. Notice in the exponent, we can factor out that k, right? So let's do that. When we do, we find that we have a simplification that occurs. All I've done here is I've said I can rewrite the denominator in terms of a negative exponent. Now I can combine these two terms because they share the same base. Now because I can do that, I can factor out this shared k in the exponent. And this 4 minus 2 will simplify to just 2. So going back to what we were told, since this is all equal to 300 over 100, that reduces to 3. We get this. Yeah. Now we're going to solve for k. We're going to do that by taking the ln of both sides. We get k, 2k is equal to the ln of 3. So k is equal to the ln of 3 over 2. I'm going to write that off over here. K is equal to the ln of 3 over 2. From here, we can take either point of data and solve for the rest of our problem, right? I would say, let's choose 2. And I want to choose 2, it's going to cancel with this 1/2 down here, right? So now, we got A is going to be equal to C E to the ln of 3 over 2. Since we've got data given to us at time equal to 2, why don't we go ahead and use that because it'll cancel with this denominator, right? That means we're going to have a nice reduction here. This is going to come out to be C to the E ln of 3. The E to the ln of anything is just that anything. So this is going to be equal to C times 3. Well, we know that the amount at time equal to 2 is 100. So C is equal to 33 1/3, 4.333 repeating. And we have found now that the equation is going to be 33.333 repeating times E raised to the ln of 3 over 2 times T. All right, now let's compare. They've reduced everything hugely all the way through. So starting off, they said, hey, let's compare our two data points. That's where they're getting this 300 over 100. And they're factoring out this 2K, right? So they're simplifying this as much as they can. And then they're saying, well, once we apply the ln to both sides, we get what K, we get that the ln of 3 is equal to 2K. Solving for K, K is going to be the ln of 3 over 2. And then using the data that we do know, we can solve the rest of this problem. So the process is long and arduous, but as you move through it a couple of times, it's going to become quick for you. Having said that, just another quick example. In this example, we've got, was it a CDU? No, it was just compounding interest problem. Okay, so in this problem, we've got an account that is incurring interest in a continuous way. So automatically, we know that the equation for the amount after some period of time is going to be your initial amount times E raised to your rate R times T. Now, what we're asked, we did this problem already, haven't we? Something similar, yeah. Yeah, we're asked to find out what R has to be in order for us to double the amount on that account after 6 years. So given our initial equation, we know that when T is equal to 6, this thing is going to be equal to 2T. We're just going to solve for R. Notice what you're going to get when you solve for R is a decimal. You're going to want to convert that into percentages. I think we had the example where it just doubles with respect to time and weren't given any other information about it. I think that's what it was. Having said that, do we have enough time? 3 minutes? No, we don't. All right, so since we've only got 3 minutes left, I'm going to go ahead and let y'all go. If you have any questions, I'll stick around. Have a good one, everybody.